Welcome to this problem-solving session. Today, we'll dive into LeetCode problem number 1664, titled Ways to Make a Fair Array. This problem challenges us to think critically about array manipulation and balancing computations. Let's explore the problem, break it down step by step, and come up with an efficient and elegant solution. Let's get started. In this problem, you're given an array of integers called nums. Your goal is to determine how many ways you can make the array fair by removing exactly one element. An array is considered fair if the sum of the elements at odd indices is equal to the sum of the elements at even indices. The input consists of the array nums, which can have a length between 1 and 100,000, and each element in the array has a value between 1 and 10,000. The output is a single integer that represents the number of ways to make the array fair by removing one element. Let's consider the first example to understand the problem better. The input array is 2, 1, 6, 4. There are 4 possible ways to remove an element, as we can remove any one of the 4 indices. When we remove the first element, nums, 0, the resulting array is 1, 6, 4, where the sum of even indices is 5, and the sum of odd indices is 6. These sums are not equal, so this is not a fair array. Next, when we remove nums, 1, the resulting array is 2, 6, 4. Here, the sum of even indices is 6, and the sum of odd indices is also 6, making this a fair array. Continuing with the other 2 indices, we find that they do not result in fair arrays. Thus, there is only one way to make the array fair in this example, and the output is 1. Now, let's look at the second example, where the input array is 1, 1, 1. Again, there are 3 possible ways to remove an element. If we remove nums, 0, the resulting array is 1, 1. The sum of even indices is 1, and the sum of odd indices is also 1, making this a fair array. Similarly, if we remove nums, 1, or nums, 2, the resulting array is 1, 1, in both cases, which is also fair. Since all 3 removals result in a fair array, the output is 3, as there are 3 ways to make the array fair in this case. Finally, for the third example, the input array is 1, 2, 3. Here, when we remove any of the 3 elements, the resulting arrays do not satisfy the condition of having equal sums at even and odd indices. Therefore, there are no ways to make this array fair, and the output is 0. Additionally, the constraints of this problem ensure that the solution must handle large inputs efficiently. For instance, the array can have up to 100,000 elements, and each element can be as large as 10,000. Special edge cases to consider include arrays with only one element, uniform arrays where all elements are the same, or arrays with a maximum length. These scenarios require careful handling to ensure correctness and efficiency in the implementation. To solve the problem of finding how many ways we can make an array fair by removing a single element, we first considered a brute force approach. The idea here is straightforward. For each element in the array, we remove it, calculate the sum of elements at even indices and odd indices in the resulting array, and check if these sums are equal. If they are, we count it as a valid removal. The steps for this approach involve iterating through every index, removing the element at that position, and recalculating the even and odd sums for the modified array. However, this method has a major downside: it recalculates the sums for every removal, and since each computation takes linear time, the overall complexity becomes n squared. This makes it impractical for larger arrays, especially given the constraints where n can go up to 100,000. While simple to understand, this inefficiency led us to explore a better solution. To address the inefficiency of the brute force approach, we turned to an optimized method using prefix sums. The intuition here is to pre-compute cumulative sums for even and odd indices up to each position in the array. These prefix sums allow us to quickly determine the new even and odd sums for the array after removing an element, without recalculating everything from scratch. The key observations are as follows. First, we define 2 arrays, even sum and odd sum, to store cumulative sums of even and odd indices, respectively. Then, if we remove an element at a specific index, the prefix sums enable us to adjust the sums for the remaining array by combining the values before and after that index. The steps for this approach involve first calculating the prefix sums for the entire array, then iterating through each index to compute the adjusted even and odd sums after removal, and finally checking if these sums are equal. This method is much more efficient, as calculating prefix sums takes linear time, and checking each index also takes linear time. Overall, the time complexity is reduced to O(n), making this approach not only faster but also scalable for large inputs. We chose the optimized prefix sum approach because it strikes the right balance between efficiency and implementation complexity. By avoiding repetitive recalculations and leveraging cumulative sums, we reduced the time complexity to O(n), which is suitable for the problem's constraints. Comparing the two approaches, the brute force method is easier to implement but suffers from inefficiency due to its O(n)² complexity, which makes it unsuitable for larger inputs. On the other hand, the prefix sum approach, while slightly more complex to implement, is highly efficient with O(n) time complexity and requires a manageable O(n) space for storing the prefix sums. The breakthrough insight here was recognizing that instead of recalculating sums repeatedly, we could pre-compute and reuse the even and odd sums using prefix arrays. This optimization not only adheres to the problem's constraints but also ensures the solution is robust and scalable, making it the clear choice for this problem. The goal of this problem is to determine how many ways we can remove an element from an array such that the resulting array becomes fair. A fair array is one where the sum of elements at even indices equals the sum of elements at odd indices. To solve this efficiently, we use a prefix sum approach, which minimizes redundant calculations and reduces the time complexity to O(n). First, we pre-compute two prefix sum arrays. The even_prefix array keeps track of the cumulative sum of elements at even indices, while the odd_prefix array does the same for elements at odd indices. As we iterate through the array, we update these prefix arrays based on whether the current index is even or odd. For even indices, we add the element to even_prefix and copy the previous value of odd_prefix. For odd indices, we add the element to odd_prefix and copy the previous value of even_prefix. This pre-processing step sets the foundation for efficiently evaluating the array after removing any element. Once we have the prefix sums, we can evaluate the fairness of the array for each potential removal. We initialize a counter, fair_count, to track the number of valid removals. For each index I, we calculate the sums of even and odd indices as they would be after removing nums, I. Using the prefix arrays, these sums can be computed directly without iterating through the array again. The sum of even indices after removal combines the even prefix sum up to I1 with the odd prefix sum from I+1 to the end of the array. Similarly, the sum of odd indices after removal combines the odd prefix sum up to I1 with the even prefix sum from I+1 onward. If these recalculated sums are equal, we increment the fair_count. Once all indices have been processed, we return the value of fair_count as the result, which represents the number of ways to make the array fair. The prefix sum approach is key to solving this problem efficiently, as it avoids the need to recompute sums for even and odd indices after each removal. This optimization reduces the time complexity from O(n)2, which would result from a naive approach, to O(n). One important insight is understanding how the removal of an element affects the indices of subsequent elements. After an element is removed, the indices of the subsequent elements shift, which is why we need to split the sums into parts before and after the removal index I. In terms of edge cases, we need to handle arrays with only one element, where no removals are possible, and arrays where all elements are the same, where fairness depends entirely on how the indices shift. The key data structures used are the prefix sum arrays, which allow us to compute subarray sums in constant time, and a simple counter variable to track the number of valid removals. The complexity of this solution is very efficient. The time complexity is O(n), because we only iterate through the array a few times, once to compute the prefix sums and once to evaluate each index for fairness. The space complexity is also O(n), as we store the two prefix sum arrays, even_prefix and odd_prefix. To illustrate the process, let's walk through an example with the input array nums equals 2, 1, 6, 4. First, we compute the prefix sums, even_prefix equals 2, 2, 8, 8, and odd_prefix equals 0, 1, 1, 5. Next, we evaluate each index. Removing nums, 0, results in sums that are not equal, so it's not fair. Removing nums, 1, also produces unequal sums. Removing nums, 2, gives equal sums of 2 and 1, so it is fair. Removing nums, 3, again results in unequal sums. In total, there is only one valid removal, so the output is fare_count equals 1. This example highlights the efficiency of the prefix sum approach and how it simplifies the fairness evaluation for each index. This solution effectively solves the problem using a prefix sum approach to achieve O(n) time complexity. Let's break it down step by step. 1. Initialization. We calculate two prefix sums, even_prefix and odd_prefix, where even_prefix, I, contains the cumulative sum of all elements at even indices up to I1, and odd_prefix, I, contains the cumulative sum of all elements at odd indices up to I1. 2. Prefix sum calculation. We iterate through the array nums to build the prefix sums. For each index I, if it's even, we add nums, I, to even_prefix. If it's odd, we add nums, I, to odd_prefix. This ensures that we have cumulative sums for even and odd indices separately. 3. Fairness check. For each index I, we compute the sums of even and odd indices after removing nums, I. The sums are computed as even_sum, the sum of even indices before I plus the sum of odd indices after I. Odd_sum, the sum of odd indices before I plus the sum of even indices after I. For comparison, if even_sum equals odd_sum, removing nums, I, makes the array fair, so we increment the count. 5. Result. Finally, we return the count of indices where removing the element results in a fair array. This algorithm efficiently computes the result by leveraging the prefix sums to avoid recalculating sums repeatedly, making it highly scalable for large inputs. Here, we have the Java implementation of the solution. First, we define the ways to make fair method that takes an integer array nums as input. The goal is to calculate how many indices can be removed to make the array fair. We start by determining the length of the array, n. Next, we initialize two prefix sum arrays, even prefix and odd prefix, each of size n+1. These will store cumulative sums for even and odd indices, respectively. In the for loop, we iterate through the array nums. For each index I, if I is even, we add the value at nums, I, to even prefix, I+1, otherwise, we add it to odd prefix, I+1. At the end of this loop, the prefix arrays contain the cumulative sums of elements at even and odd indices up to any given point. Then, we initialize a variable count to 0, which will keep track of how many indices result in a fair array when removed. Another for loop processes each index I to calculate the sums of the remaining even and odd indices after removing nums, I. Using the prefix arrays, we derive even sum and odd sum efficiently. The even sum is calculated as the sum of the even prefix up to I, combined with the odd prefix from I+1 to the end of the array. Similarly, odd sum is computed as the sum of the odd prefix up to I, combined with the even prefix from I+1 to the end. Finally, we check if these two sums are equal. If they are, we increment the count variable. After completing the loop, the method returns the value of count, which represents the total number of indices that can be removed to make the array fair. This concludes the implementation. By leveraging prefix sums, the solution efficiently computes the required values without recalculating sums repeatedly, ensuring optimal performance. The result is an elegant and concise approach to solving the problem within the constraints. Here, we are given the input array nums equals 2, 1, 6, 4, with a length of 4. To help us solve the problem, we initialize two prefix sum arrays, even_prefix and odd_prefix, each with an extra space to simplify index calculations. Both arrays start as 0, 0, 0, 0, 0. The first step is to calculate the prefix sums. As we iterate through nums, we update the prefix arrays based on whether the index is even or odd. For index 0, which is even, we add nums, 0, to the even prefix, giving even_prefix, 1, equals 2. At index 1, which is odd, we update the odd prefix, resulting in odd_prefix, 2, equals 1. Index 2 is even, so we add nums, 2, to the even prefix, making even_prefix, 3, equals 8. Finally, at index 3, we update the odd prefix to odd_prefix, 4, equals 5. The final prefix sums are even_prefix equals 0, 2, 2, 8, 8, and odd_prefix equals 0, 0, 1, 1, 5. Now, we determine how many ways we can make the array fair by removing one element. We initialize count to 0, which will track the number of valid removals. Starting with index 0, we remove nums 0 and calculate the sums for the even and odd indices. The even sum is formed by combining the even prefix up to index 0 and the odd prefix from index 1 onward, giving even underscore sum equals 5. Similarly, the odd sum is calculated as odd underscore sum equals 6. Since these are not equal, the array is not fair after this removal. At index 1, removing nums 1 gives even underscore sum equals 6 and odd underscore sum equals 6, which are equal, so we increment count to 1. At index 2, removing nums 2 results in even underscore sum equals 6 and odd underscore sum equals 1, which are not equal. Finally, at index 3, removing nums 3 gives even underscore sum equals 8 and odd underscore sum equals 1, which are also not equal. After checking all indices, the total count of fair removals is 1. The output for this example is 1, meaning there is exactly one way to make the array fair by removing a single element. Now, let's look at another example with nums equals 1, 1, 1. The input array has a length of 3, so we initialize even underscore prefix and odd underscore prefix as 0, 0, 0, 0. Calculating the prefix sums, we see that index 0 is even, so even underscore prefix 1 becomes 1. At index 1, which is odd underscore prefix 2 updates to 1. Finally, at index 2, the even prefix becomes even underscore prefix 3 equals 2. The resulting prefix sums are even underscore prefix equals 0, 1, 1, 2, and odd underscore prefix equals 0, 0, 1, 1. Next, we analyze fairness after removing each element in nums equals 1, 1, 1. Starting with index 0, removing nums 0 gives an even sum of 1 and an odd sum of 1, so the array is fair, and we increment count to 1. At index 1, removing nums 1 results in an even sum of 1 and an odd sum of 1 again, so we increment count to 2. At index 2, removing nums 2 also yields equal sums for even and odd indices, so we increment count to 3. The total count of fair removals is 3, and the output for this example is 3. Finally, consider the array nums equals 1, 2, 3, 4, 5. The step-by-step analysis follows the same logic as the previous examples. After removing each element and calculating the even and odd sums, we find that there is only one way to make the array fair. Therefore, the final output for this example is 1. The time complexity of the solution is determined by two main steps. First, we calculate the prefix sums for the array. This involves iterating through the array nums, which has a size of n. During this single pass, we compute two prefix sum arrays, one for even indices and another for odd indices. Since each pass through the array requires linear time, this step has a time complexity of O(n). Next, the algorithm iterates over each index I in nums to simulate the removal of the element at that position. For each index, the even and odd sums after the removal are calculated using pre-computed prefix sums, and these calculations are done in constant time, or O(1), for each index. Iterating over all n indices, therefore, takes O(n) time. Combining these two steps, the overall time complexity of the solution is O(n) plus O(n), which simplifies to O(n). Now, let's analyze the space complexity of the solution. The algorithm uses additional space to store two prefix sum arrays, even underscore prefix and odd underscore prefix. Each of these arrays is of size n plus 1, where n is the size of the input array. As a result, these arrays collectively require O(n) space. In addition to the arrays, the algorithm uses a few scalar variables such as n, count, even underscore sum, and odd underscore sum. These variables are independent of the size of the input and require constant space, or O(1). Therefore, the total space complexity is dominated by the prefix sum arrays, leading to an overall space complexity of O(n). Let's compare this optimized approach to a naive brute force solution. In the brute force approach, for each index I, the algorithm would simulate removing the element at that index and recalculate the sums of even and odd indices for the resulting array. Recomputing these sums requires O(n) time for each index, and since this process is repeated for all n indices, the total time complexity is O(n) squared. On the other hand, the optimized solution avoids redundant calculations by pre-computing the prefix sums. Using these pre-computed values, the even and odd sums after removing an element can be determined in constant time, or O(1), for each index. This reduces the overall time complexity to O(n). Importantly, this optimized approach maintains a time complexity of O(n) across the best, average, and worst cases, as the algorithm always processes the entire input array to compute prefix sums and iterate through the indices. Finally, let's validate the time and space complexity mathematically. During the prefix sum computation, the algorithm iterates through the array once, resulting in a time complexity of O(n). Similarly, the iteration over all indices, where constant time operations are performed for each index, also contributes O(n). Adding these together gives a total time complexity of O(n) plus O(n), which simplifies to O(n). For space complexity, the prefix sum arrays are the primary contributors, requiring O(n) space to store cumulative sums. Since no other significant space-dependent structures are used, the overall space complexity remains O(n). This analysis confirms that the solution is efficient in both time and space usage, making it well-suited for large input sizes. When solving this problem, there are several common mistakes to avoid. First, it's crucial to calculate prefix sums separately for odd and even indices. A single cumulative sum won't work because the problem requires you to evaluate the sums for both even and odd indices after removing an element. Another frequent issue is modifying the array during iteration. If you remove elements directly from the array, it alters the indices of the remaining elements, which can lead to incorrect calculations and unpredictable behavior. Additionally, relying on a brute force approach is a major pitfall. Checking all possible removals with O(n²) complexity is inefficient for large inputs, such as arrays with 100,000 elements, and will likely result in a time limit exceeded error. Finally, watch out for off-by-one errors. Mixing up zero-based and one-based indexing when calculating prefix sums can easily happen, and it leads to invalid results because the sums for even and odd indices will be misaligned. Another critical mistake to avoid is neglecting edge cases. For example, arrays with just one or two elements, or arrays where all elements are identical, can behave differently from larger, more varied arrays. If these cases aren't handled properly, you risk your algorithm crashing or returning incorrect results. From an interview perspective, this problem is a great way to demonstrate your ability to recognize patterns in array manipulation, such as separating even and odd indices using prefix sums. Additionally, it tests your skill in optimizing space usage. Transitioning from O(n) space for prefix sums to O(1) space is a valuable optimization to highlight during discussions. Interviewers may also ask how you handle edge cases, so be prepared to explain your approach to scenarios like empty arrays or single-element arrays. Lastly, make sure you're ready to articulate the time complexity of your solution. Being able to explain why your approach runs in O(n) time and how you avoid nested loops shows a strong grasp of the problem and its constraints. This type of problem is closely related to several others on LeetCode, which can serve as excellent practice for building your skills. For instance, LeetCode 560, subarray sum equals k, also relies on prefix sums to optimize calculations involving arrays. Similarly, LeetCode 724, find pivot index, involves dynamically calculating left and right sums for each index, which is conceptually similar to balancing sums in this problem. Another related problem is LeetCode 238, product of array except self, where prefix and suffix products are used to achieve the result without extra space. Finally, LeetCode 1991, find the middle index in array, deals with balancing left and right sums, making it another great example to study. These problems share common patterns and techniques, such as prefix sums and balancing calculations, which can help you develop a deeper understanding of array manipulation strategies. There are several approaches you can take to solve this problem, each with its own trade-offs. The brute force approach involves calculating the left and right sums for even and odd indices after removing each element. While this method is straightforward to implement, it's inefficient with a time complexity of O(n²), making it unsuitable for large arrays. A more efficient strategy is the prefix and suffix sum approach, where you use prefix sums to calculate cumulative sums for even and odd indices. After removing an element, you can update the sums dynamically using the prefix and suffix. This approach has a time complexity of O(n), but it requires careful handling of indices and edge cases. The most efficient solution is a single-pass approach using running totals. Here, you maintain running totals for the left and right sums while iterating through the array. This method achieves O(n) time complexity with O(1) space, but it is more complex to implement and debug due to the intricate calculations involved. Each approach has its place depending on the problem's constraints and your familiarity with the techniques. Great work! In this session, we tackled the problem ways to make a fair array and explored how to use prefix sums for an efficient solution. Remember the key lessons about balancing computations and leveraging cumulative techniques. Thanks for watching, and don't forget to like, subscribe, and keep practicing to sharpen your problem-solving skills. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!